Hi, my name is Matt Maslow. I'm at Scripps Oceanographic. I'm here to present work led by Yanjiao Wei on optimizing mooring placement to constrain Southern Ocean fluxes. And this is a collaboration of the Southern Ocean Observing System working groups on Southern Ocean fluxes and observing system design. Sarah Gilly, Veronica Tamzet, Seb Swart, Doc Chen, Louise Newman also contributed to this. Now, there's a lot. For brevity, I'm only going to go over a case, some specific examples, results from this paper that Yan Zhao recently published. There's a lot of more information and caveats and things to discuss. And if you're interested, you can find them at this paper. It's a recently published in JTech. This is the title: Optimizing Mooring Placement and Constraint Southern Ocean Air Sea Fluxes. Now, Southern Ocean is a big void for air sea flux measurements. There's the OOI mooring, the Southern Ocean flux site mooring. We'll be talking a bit about the SOFS mooring today, so that's just south of Australia. This OOI is no longer in the water, SOFS still is, but you can see this is July ship measurements, which give you enough information to get estimate latent heat flux. There's nothing there. So to remedy this problem, Doc Chen presented at a SEUS meeting in 2018 the idea of a big ring of moorings around the Southern Ocean, around Antarctica, to constrain fluxes, and other countries have shown interest in contributing this as well. But the question came up, well then, where do you put these moorings? Do you just distribute them equally? Well, we looked at reanalysis statistics to try to understand them. So the main tool in this talk is the JRA 55 net heat flux. Red is warming the ocean, blue is cooling it. This is the mean. I can talk about the mean. We're going to talk about the variability around that mean. And so this is the standard deviation. This is the signal that we want to try to constrain with our moorings. You can compare how JRA is doing compared to the SOFS mooring. To this slide. JRA is the blue line. SOFS is the red line. This is the integrated heat flux around the Southern Ocean. Oh, I'm sorry, at the SOFS mooring location. And the time series of that, you can see they track quite well. But when you difference them, you see there's biases. There's information the moorings can provide to improve the reanalysis. JRA is coming in lower. And in the paper, we repeat everything we've done here with ERA as well, but ERA interim. But that's for brevity, I'm not going to show those results. Okay, so the integrated heat flux in the Southern Ocean is this black line. This is from JRA. And you can see it has a large seasonal component. We decided we're going to take the assumption that the seasonal cycle, part correlated to the sun, is relatively well known, and we remove that, and it's semi-annual harmonic, and we look at the blue line, the residual. What's going on there? We want the moorings to tell us about the deviations from the seasonal cycle. We can further decompose that into interannual variability and high frequency variability, less than 1 year. That's this blue line versus the red line. We'll just talk about the high frequency now, but we talk a little bit about the low frequency as well. First, if we look at it, we can look at the dominant modes of variability by empirical orthogonal function decomposition. This is the dominant mode of high frequency variability. You can see it has a wave 3 structure. The second most dominant mode, explaining 6% of the variance, has a wave 4 structure. So there's these large scale wave-like modes that are dominating the variability, and we want to capture that. We can also look at the interannual variability, the low frequency modes, and you see we have a trend mode, and then we have a mode that correlates well with ENSO, and then we have some other modes too. And so in the paper we discuss some of these modes, but for the point of this paper, we're going to say, for the point of this talk, I say just where do we put the moorings. So instead of looking at these modes and trying to understand them, we're just going to say what point best explains the variance of every other point in the Southern Ocean heat flux. So our method is as follows. Here's the signal, the standard deviation. For every point in the Southern Ocean, well, I'm sorry, between 35 south and 65 south. So every point 35 to 65 south, we take the covariance of that with every other point and normalize it by the points variance itself, because we're not trying to explain the signal correlated with the mooring. We're not trying to explain the signal at the mooring spot. That's why we normalize it. We're trying to explain the covariance of the heat flux in general, the variance of the heat flux in general. So one might think of this as a formal mapping error in objective mapping speak. So here's the standard deviation. If we look at the variance that can be explained by 1 point, we find this is the one that can explain the most. This is where we put the first mooring. And if you look at the correlation of the rest of the Southern Ocean with that, you see, well, this looks a lot like that first EOF mode. It looks a lot like that wave 3 pattern. So this point is best is capturing that mode. So we do this iteratively. Now we have a mooring here. We can take this signal that is covariant with that and remove it, and that's this plot. So this was our original signal. This is our new signal. This is our new unconstrained signal. You can see right where the mooring it was, or is now. It's quite reduced. And we say, well, where's the next point that explains the most variability of the Southern Ocean heat flux? And it ends up being very close to it, just about 30 degrees away. And you can see by the correlation, it's also kind of a mode 3 pattern. It's offset though. And so we put the mooring there. We subtract that signal off. We do this again, and we can repeat this over and over again until we find, until we beat down the noise. We explain the signal, and we do this for 8 moorings, and these are the 8 we find. So this was the first one. This is the second one. We find 6 more, and we can look at, all right, well, this is the original signal. If we try to reconstruct heat fluxes with just these 8 points, we get this signal. And when we remove that, this is the still unexplained signal. Now I said 35 to 65, so you can see there's still a lot of variability that we weren't able to capture around Antarctica. We also mentioned in the paper that if we had 2 more sites, we put them here, depending on if other countries want to contribute to the big ring, then maybe we can get 10 moorings. We were just dreaming. But we provided a method, and with this method, we can quantify that we're 8 moorings are able to, and these are the 8 moorings, 1, 2, 3, 4, etc., that we can explain 25% of the net heat flux variance of the Southern Ocean, the high pass net heat flux variance. Now, ADOFs explain 37%, so this is pretty good. They're saying, the best you can do with 8 degrees of freedom is 37%, and with 8 moorings, we can actually constrain 25%. And those same 8 moorings designed to capture the high frequency component also capture about 40% of the low frequency component. Now, the low frequency component, if you wanted to just design your array to capture that, you could get up to 45%, but you do pretty well designing just for the low frequency. There are caveats. For example, low frequency, the high frequency looks pretty similar whether you use JRA 55 or ERA interim, but the low pass looks quite different. For example, in ERA interim, if you carried out this method on ERA interim, you'd have a mooring here, whereas if you carry it out with the ERA 55, you can mooring here. So the interlinear variability statistics are different between these reanalysis products. And there are other caveats we talk about in the paper. But here's the summary. We envision flux moorings to be one very important part of the global ocean observing system. That they really will complement autonomous vehicles. They will complement satellite measurements and ship measurements, and together with data assimilation, will help fill the gaps and allow us to best constrain the Southern Ocean fluxes. So we developed a framework for where to put these moorings, given that that there already is a global observing system. We in the paper we talk about, well, knowing there's the software, should we put these? And we talk about some of these caveats, including the fact that the reanalysis products are not perfect, and different ones give you different signals. But yes, in summary, 8 moorings can give us 25% of the high pass or 45% of the low pass, and we present this algorithm in this paper in JTech. So happy to discuss more. I'll be around. I'll try to answer questions in the open discussion, and also note that this can be applied to other regions too. And so thank you for listening.